Steven Yuan, founder and the CEO of StorageX.ai. Today, I'm going to talk about the efficiency of data-centric computing. So today's world, we're facing a lot of challenges right now. We have a lot of issues about the big data, and we have a lot of issues about the fast data as well, especially for the recent development of large language models such as GPT-3 and GPT 3.5, ChatGPT, and GPT-4. So at this time, we're going to talk about how we're going to optimize compute and how we're going to optimize data movements as well. So today, I'm also going to talk about where the different computer resources are going to fit and what we work on as a smart data lake. And we're going to conclude with a slide to talk about a summary. So big and fast data really, it's happening in today's world right now. On the left hand, we can see this is Data Never Sleeps 10.0. These slides has been updated for every year for past 10 years. So by looking at this, we're going to see 2022, the amount of data generated in every minute. Google has 5.9 searches. YouTube have 500 hours of video uploads, and the stream video has about 1 million hours. And Facebook has about 1.7 million contents shared, and Zoom has 100K hours of meeting happening in 1 minute. So this world really generates a lot of data. But I look at this 2020, we had almost about 40 ZB of data, and by 2025, this is going to grow another 4x. It's about 163 ZB of data. However, in these 5 years, we're going to see a lot of increase. In another hand, that amount of data need to be analyzed. So that amount of data growth needed to be analyzed, it's going to be about 100x. That is much bigger than what we see the data growth by itself. So in this amount of data, 20% of it going to be real-time data. And by that time, we're going to connect a lot of 75% of global population. So really, there's a lot of data growth and analytics requirements by 2025. So ChatGPT start to occur end of 2022. That we see that there are large models, language models, to show a big improvement in the performance in intelligence. So by looking back, starting from 1950, 1960, we had a really small models, or by that time we still called it machine learning, or maybe something earlier. And in past 50 years, that really it grows every 2x per year. It's about the same speed as Moore's law. But in the last 5 to 10 years, the larger model really grows by 10x by every year. So this creates a challenge of the balance for the compute and the data by itself. So the amount of data we need to train these models and the parameters of these models generated, that needed to be, computed and trained for the training itself, for the inference, etc. So the balance of these hardware resources and the data itself become very predominant issue. And by that scale, in next 1 or 2 years, our model may grow another 10 or 100x. So why we're looking at these kind of large language models in the industry? In the past few years, people discovered that scaling unblocks the emergent ability in language models, really. So we see chain of thought start to prompt, and the performance itself jumps, when the model larger than certain size, especially when it starts to be over the 100 billion parameters. And we're seeing a unexpected emergence of the capability coming out of their supersized models that is not presented in the smaller model. So we call these as emergent ability for the large model itself, and the intelligence of the model has been proven by GPT 3.5, or we call it ChatGPT at this time. And the GPT-4, similar thing that, another level of improvements in the performance really started to occur. So by looking back, better computer really enables bigger model trained for longer, and a better storage really enables the learning from more data. So we look at this ChatGPT itself, or GPT 4.0, utilized about last 20 years contents, shared contents from internet. And that's huge amount of data that's being used for training. And now we have about 100 million people sign up for the first month to use the ChatGPT. There's a lot of access at the same time as well. So that challenge, this really creates a challenge for the computer resources and the data itself as well. So how are we going to optimize compute? We really needed to optimize the data movements first. So on the left hand, we see that data hierarchy by itself. From the CPU all the way down to level 1, level 2 cache, and the DDR itself, and the storage class memory, and the SSD, and both storage, like for example, like a disks and cloud. Every level has a log scale increase in the capacity itself. And the dashed line over there below DDR is really a dividing layer for memory itself and a storage. So we usually call it volatile memory and a non-volatile memory. So the compute itself, it's really represented by the data movements. So we see there's a lot of data occurs on the storage side, and start to moving up to the DDR side, and then cache side, and then that's where CPU that does all the computing work at this point. So we look at these closely, that how much of the energy has been consumed by compute itself versus by the movements itself. So we look at this really closely, that actual consumption of the computer power really only occur that a small percentage of the total energy consumed. For example, this is one example presented in ISCC 2014 that shows a add function only consume less than 1% of the total energy, and the rest of 99% is almost all wasted at the data movements. So this really presents a opportunity and a question and opportunity for us, that where we needed to optimize the compute. We really needed to optimize the data movements first. So by looking at that, then we look at back to on the left-hand side on the data hierarchy, that SSDs and the disk and cloud location, that really where the large amount scale of the data occurred and it resides. That's a PB and the EB levels of data over there. That's the perfect area for the data analytics and data mining. So in these slides, I'm going to talk about the different computer resources. So we have, by looking at this, we have fast data and the big data on the left hand, fast data on the right hand, and the big data. So, and I divide that by the computer intensive workload, and on the right hand, it fits for the data intensive workload. Okay. So computer node, CPU and GPU, we use small and this is the area that usually fits in gigabyte level of data, and on the HBM or DDR itself, small but fast. And in the middle, that where the network computing that occurs, IPUs, smart NICs, and there are a lot of compute done in the network by itself. For example, infrastructure stuff, security, compression maybe, and other stuff we call orchestration stuff as well. So on the right hand, that where the big data resides. And there's a lot of storage nodes, SSDs, hard drives, etc. So that's a perfect area for the computational storage. We call it CS. And there's a lot of near data processing can be done, data acceleration can be done, federated data processing can be done, and the AI and machine learning can be done over there as well. So by looking at that, right hand in the big data area, computational storage will present a very good opportunity over there. So that's where the dumbbell effect shows that today dumbbell effect causing a very high compute cost. And by looking at this on the top, moving data really creates a lot of heavy traffics and a long latency. And for example, we move like 1 petabyte of data. If we set that over the network versus we ship them over the truck, I think the second option is faster at this point right now. So that's where the problem occurs. If we needed to use large amount of data to generate the results and also to create applications, and the time and the energy wasted on the data movements will be very big. Okay. So on the bottom side, instead moving the data itself, we can move the compute and make the return the results. That's where the lower traffics and the lower latency occurs. So in conclusion, that the compute efficiency is really proportional to the compute power, data acceleration, I/O bandwidth. However, the data volume and the moving distance really make a negative impact. So by looking at that, data-centric computing is really a key solution. So this is a typical structure of a system at today's world. And we have CPU and GPU servers on the left hand and the storage servers on the right hand. There's a bunch of networks connected in the middle. And the latency really represents the application response time, how many people can access at the same time, and the traffic as well, etc. So when Newman's architecture really requires large amount of data movements. If there's a bunch of videos needed to be processed and then needed to extract from the storage node and put them on CPU and GPU node. So this really creates high cost of the network bandwidth, time, and power consumptions. And that's where the problem really is. By looking at this architecture, we're going to see that the problem could occur anywhere that has a bottleneck. For example, if the network has issues, not good enough, even we have really high performance, powerful GPUs on computer node, but then we cannot utilize them. On the other hand, if we have large amount of data needed to be moved and the network bandwidth is even high, but we're still going to have a lot of issues over there. So that's where the moving results instead of data helps. So we needed to compute really near the data, reduce data movements, latency, and it can also reduce the TCO drastically. And by looking at that, we're going to streamline the throughput. So data lake, performance critical functions, AI inference, other applications can be done really in a streamlined throughput. So data center right now today is moving into a disaggregated systems. Yesterday we have a computer-centric architecture, so we call it direct attached system. So we see that the regular servers have CPUs, GPUs, DDR, and SSDs, and we have them connected to the network itself. And today, in the future, there's really a data-centric world that we have a disaggregated system all over the place. We have CPU servers, GPU, independent GPU servers, and we also have the data servers as well. So the idea really storage, is for the storage itself is really to transfer to the smart data lake. That's where StorageX.ai has been working on. So computer near the data for low latency that overcomes data gravity and creates a distributed computing. It's really for the real-time analytics. So how the smart lake looks like and where the application is. So smart data lake can be used in different areas. It can be used on the edge for the edge computing and the core area as well. So we see that on the right hand is a typical storage server. So we have a lot of drives in that and keep the data, and we only look at the most of the time for the past 50 years. And when we look at the storage, we look at the capacity, we look at the cost, we look at the I/O performance, and we look at the power consumptions. However, when we transfer this storage rack to a smart data lake, really transforming a storage rack into the data service stack. So we can put a lot of applications in there: computer near data, data acceleration, real-time analytics, flexible applications. There's a lot of things can be done over there, especially for the AI workloads. And that requires a lot of data movements and a lot of inferences work can be done over there. So in conclusion, data-centric computing really creates a lot of compute opportunity for this world. And the market we're looking at really is a storage plus a compute market. It's about $180 billion or $190 billion by 2026. And the growth rate for the accelerator is about 36% from 2021 to 2026. And the storage side is about 15% CAGR. So in conclusion, data-centric computing is really very important for data-intensive workload. So by looking at that, we look at it, compute-intensive and data-intensive, two different worlds, but data-intensive really represents a lot of work at this point. That overcomes a lot of data gravity. And moving compute closer to a data is more efficient than transferring large amount of data. So by using federated data processing, that allows for better system efficiency. And we know that when we lower down the data size, that will reduce the network traffic, creates less data movements and less time consumed, and have lower latency as well. And it also for the data center players, they're going to see improve the total cost of ownership. In conclusion, this architecture will help tackle the coexistence of the big and faster data challenges. So that's where StorageX.ai comes into play. We help to provide the total solution for data-centric computing. Thank you so much. And please take a moment to rate this session, and your feedback is welcome. Thank you so much.